So, welcome to this module on non-Newtonian fluid flows. What I will be doing is an introduction to the subject of non-Newtonian fluids. What an introduction would mean is that I will take material from these two textbooks. Most of the material would be taken from the second one, because the second one is a little bit more modern adaptation of the first one. So, the material would be mostly common, but what I have seen in my classes is that the second one is a bit easier to follow. So, what I will be following is closely the second one with some materials taken from the first one, and this is designed to be an outline, which means that this is not a full course. So, this is like a 8-minute highlight of a 90-minute match, in that sense. So, this is designed to be to touch most of the topics, but not get into too many details. Of course, you will find the details in the textbooks, and you can of course contact me. Okay. So, the basic fluid mechanics, what you have learned maybe earlier, is Newtonian fluid mechanics, which means you are trying to solve this sort of equations. One is the continuity, followed by the momentum equation, followed by something which is called a constitutive equation. So, in Newtonian fluid mechanics, what you try to solve is the continuity, the momentum, and the momentum equation is coupled with something known as the constitutive model, which actually is a relationship between the stress and the strain rates. So, on the right hand side you have del of V, and I have used the under bar for all the vectors, a double under bar for tensors. So, that is the notation that the second book follows. So, you solve this set of equations, and in Newtonian fluid mechanics you are solving for the pressure and the velocities. You effectively can combine, take this equation and put it here when you get the Navier-Stokes equation. So, at the end what you have is 4 equations and 4 variables, because there are 3 velocity components and 1 pressure, and you have a matched number of equations and unknowns. So, you can solve it. But in non-Newtonian fluid mechanics, what happens is I cannot assume this to be true anymore. So, the simplicity of the Newtonian model, which says that the stress is just directly proportional to the bracketed term, which is also known as the rate of strain, which you might have heard already. So, this simple proportionality breaks down for non-Newtonian fluids. The way it breaks down is different. So, different non-Newtonian fluids, the way this thing breaks down is different. So, what we first need to do is characterize the various non-Newtonian fluids that we have. That is, just simply saying that it is a non-Newtonian fluid does not suffice. You need to say what type of a non-Newtonian fluid it is. So, the first thing is characterization, which I will go in some detail. Then after the characterization I will talk about the models, and I will develop the models as they were developed in history. So, in that historical fashion, so that you can see which models can predict this, what models can predict that, and there will be a continuum series of models going on in this module and the next module. So, since we do not have this, and then I was talking about characterization, the first thing about characterization is, so you should feel free to ask me questions and stop me in between. First thing about the characterization is that you have a, let us say, a non-Newtonian fluid, and what characterization would mean, like in materials, you have to poke and prod it in some manner. So, you have to impose certain things on that non-Newtonian fluid and see what response it gives. Now, the typical ways to poke a non-Newtonian fluid, if I ask infinite number of people, there would be infinite number of ways. So, what rheologists do and what non-Newtonian fluid mechanicians also do is they choose a set of flows called standard flows. So, when we talk about a non-Newtonian fluid, suppose we have an unknown non-Newtonian fluid, we have a certain set of flows which are standard, and we only use those flows and impose those flows on the sample of non-Newtonian fluid, and then record the response of that fluid, and then try to understand from the response that it generates what sort of a non-Newtonian fluid is it. Like, is it close to this family or that family or that family. So, we demarcate the families based on the responses from these standard flows. So, the standard flows of non-Newtonian fluids Now, so these standard flows which are used for characterizing a non-Newtonian fluids there are certain characteristics that these standard flows should have. One is they should be simple enough to realize experimentally. So, you are trying to have a non-Newtonian fluid sample and you want to understand the characteristics. So, you have to put it in some form of experiment. So, the standard flows has to be realizable experimentally very easily, and the standard flows also should be easy to analytically for you to be able to compute things with it. So, the standard flows that people typically use, the first one is the simple shear and its variance. The simple shear flow of course is given by the velocity profile in this manner. And you might guess that the simple shear is nothing, but you have a fluid sample held in between two parallel plates and you are moving one parallel plate past one another. So, that is the first type of standard flow that you use to characterize a non-Newtonian fluid. Let me put it up a little bit. Little bigger? Should I use a different color? Okay. I think none of the colors are good enough, so I have to do with this. So, I'll write it as big as possible. So, we were in shear flows and I had the diagram of two parallel plates, and the velocity profile of a shear flow you already know is all I am talking about is simple shear flow, where I will talk about the variance one by one. Of course, we are in 3D geometry, so there will be three velocity components. Now, x1, x2 and x3 have typical meanings in shear flow. x1 is the flow direction, so this would be my x1, and the x2 is the gradient direction, which is why the velocity profile in the x1 direction is proportional to the vertical position of the point. Now, notice that the shear rate here is actually can be a function of time. So, even though we are talking about simple shear flow, this standard flow would have several variants based on what time function we impose on this shear, and we will come across all those variants one by one. So, this is the first type of standard flow that we use for characterizing non-Newtonian fluids, and what turns out is that a simple shear flow or any kind of shear flow is really a mild type of flow. So, mild and strong are relative terms to use. The next standard flow that we have, the extensional flow, is much more stronger, in the sense that if I have 2 points separated by, let us say, a distance, some distance L in shear flow, in the limit of long time you can show that the separation distance between the 2 points would go linearly in shear flow. Whereas, in the next standard set of standard flow, that is flows that do not have rotation at all and elongational flows. So, the next set of standard flow is one in which there is no shear. So, essentially there is no rotation at all. So, these are purely stretching type of flows. The most important extension elongational flow, the most useful elongation flow in various applications is what is known as the uniaxial extensional flow. Write the term right. And the velocity profile for when you have a uniaxial extensional flow as you would see from the velocity profile. This uniaxial extension flow is a peculiar flow in which if you draw the streamlines in the x1 and x3 directions, the streamline would go like this, and you can figure out from the flow profile itself that the flow is devoid of any rotational motion. So, these family of flow of extensional flows, which is also a kind of standard flow for non-Newtonian fluid characterization, is actually free of rotation. So, these are rotation free flows. Uniaxial extension is one in which you are getting extended in only along one axis, that is the third axis along x3, and all the other two axes fluid is actually getting compressed. So, which means that the flow is like compressed in this plane and it is coming out. Now, there are variants to the elongation flows as well. So, you can have uniaxial extension, which is important, and then you can have some other variants. One of them is the planar version of the extensional flow. The planar is again very similar to a uniaxial extension, except that the velocity profile only has two non-zero components. So, the main difference between the two types of elongational flows that I have written on the board is that here you have velocities in all directions. Here you do not have you have a stretching in one direction and an equivalent amount of compression in another direction. So, it is like you can draw this thing on the plane itself. So, that is why it is called planar elongation. And there is a third variant of this, in which this extensional rate that we have, if you just flip the signs. So, if the extensional rate is negative instead of the usual positive convention, then what we have is something known as biaxial stretching, in which you are getting the fluid element stretched in two directions and compressed in the third direction. So, that I am not writing it here, it is called biaxial stretching, and you can of course go back to these books and find details of all those standard flows. Now, these standard flows, what we then have is, once we have a non-Newtonian fluid sample, we will impose these standard flows on the sample and basically measure stresses. So, we will have a flow, and then we will have some measurement device to measure the stresses. Now, when we do measure the stresses, there is one little subtlety that comes out for incompressible fluids. So, the total stress tensor of a fluid, when you measure stresses, you will only get the total stress tensor. So, the total stress tensor has a pressure contribution and the contribution from the deviatoric stress. Deviatoric stress is produced of the fluid elements. Now, if you notice this for a uniaxial extension flow, this would mean a stress tensor like this, in which I have the diagonal elements to be non-zero and all other elements to be 0. Now, the problem is that this is a small subtlety in the field. When you measure stresses, you are getting a combination of P plus tau 11, P plus tau 22 and P plus tau 33. Now, for a gas, if there is a gas, then if you measure the density at a certain location, you can actually measure pressure from an equation of state. For an incompressible fluid, it is very hard to separate this pressure and the tau components out, because in an incompressible fluid, in a truly incompressible fluid, the density is not affected even if you increase pressure or decrease pressure, which means that it is kind of indeterminate in some sense, which is why when we try to measure stresses from non-Newtonian fluid experiments, we do not really measure stresses. What we measure is differences between these terms, and these differences you might see if you take differences between this and this and then this and this. These differences have special names. These are called first normal stresses and second normal stress coefficients. I will of course define them later, but once you take differences, these differences are independent of the pressure. So, you do not have the contribution from the pressure, and you can actually rely solely on the differences of deviatoric stresses. So, that is something that we have to keep in mind while doing experiments with non-Newtonian fluids, which are also incompressible, which is true in all almost all chemical engineering applications. So, with these standard flows and with these stresses that I have introduced, yeah, I will come to it again. So, I will have to refer to it again, because I have to define material functions, which will depend on these. So, with these standard flows, what we now come to the point is So, we have different types of non-Newtonian fluids and we impose these standard flows on them. Now, what are the type of responses that we see? Now, when I come to this point, you might realize, being a polymeric person, I will mostly be talking from the point of view of typical polymeric fluid dynamics. Both the references that I have are more focused on polymers, because that is a non-Newtonian fluid which we have most experience with. Now, of course, this workshop is is a compendium of all sorts of complex fluids. So, responses might be a little different if you have a slightly different non-Newtonian fluid, but then however, the modeling aspects will be, there will be some generality between the modeling aspects of the various fluids. Anyways, so now that we have defined the standard fluids, standard flows, the next thing to realize is, once you have a standard flow and once you have a fluid, notice that for a non-Newtonian fluid, your viscosity is no more a constant, which it used to be the case in terms of when we had a Newtonian fluid. There the viscosity is a constant. So, what was a material property, viscosity was a property of the material, that material property now, since it is not a constant, that material properties will be, and you will see that it is a function of the shear rate or the extensional rate that you impose. So, in some sense that material property has changed to a material function, which is why we have this term, whole term of material functions, and material functions are defined with respect to the standard flow that it is adhering to, which means that we have a shear and we have variance of shear. Let me first summarize the responses, so that you get a overall feel of all the responses that you might get in non-Newtonian fluids. So, first we have the shear flow, which is a standard flow, and we can have several variants. As I said, there is something called a steady shear. So, if you notice steady shear, if you try to plot it on a graph, what we are doing in steady shear is we are imposing a shear rate and we are measuring the stresses basically. Now, when we say steady shear, I am just maintaining a constant shear rate, then that is what is meant by steady shear. Sorry, I will just follow the same notations as the books, and this is some steady shear. I am maintaining a constant shear rate. For this constant shear rate, a typical non-Newtonian fluid response, well, before I go to a non-Newtonian fluid, if I have a constant shear rate, if I have a Newtonian fluid, the typical response of a Newtonian fluid would be some value of stress which is proportional to the strain. Now, even for non-Newtonian fluids, if it is steady, there will be some other value, but it is essentially a constant value. So, for steady shear, I have a constant shear imposed on the system, I will get a constant value of the stress. This is stress versus time, tau to 1, because we are talking about shear. This is the shear rate versus time. Now, things get more interesting when you have other experiments which involve transients. So, the first transient that you can impose is a shear rate growth. So, this is called the stress growth experiment, and what you have is that the shear rate first was constant at 0, then suddenly at t equals to 0 you impose some shear rate on it which is non-zero. Now, based for these kind of shear rate profile, I will probably draw the shear rate profile in a different color. So, for the shear rate profile, if you argue that what would it be for a Newtonian fluid? Well, a Newtonian fluid is just proportional to the flow rate, the stress is proportional to the flow rate, which means it will just follow closely the shear rate profile that you give. So, for a Newtonian fluid, you just get this sort of a profile. For the typical non-Newtonian fluid, however, I mean for the general polymeric type liquids that we have, which again I reiterate that we have most experience with, this general polymeric liquids, if you measure the shear stress, this response might be varied like this, or the response might be like this, and you will notice that both of the responses, they tend towards a steady state, but there is a lot of transient phenomenon that is happening. Now, this is where the fun begins, in the sense that the first one was steady shear. That is not a big challenge. I will talk about some subtleties about steady shear, but essentially when you are looking at non-Newtonian fluids of the type of polymeric liquids, you should have a model which ideally should capture these sort of things, this sort of experiments and this sort of responses, where you have sometimes an overgrowth, overshoot, sometimes you have some curve reaching to a steady state monotonically. Now, the inverse of this experiment is something where I decrease the shear rate suddenly. So, I can have a higher shear rate initially, which is decreased by a certain value. So, this is called the stress relaxation experiment. So, I just mentioned this is stress growth. This is steady shear. This is stress relaxation. So, in stress relaxation, you are suddenly releasing the stress, which is why it is called stress relaxation. And then if you notice the response of the stress, since it had a earlier steady state, the stress was at an earlier steady state value. If it is for Newtonian fluid, it would just be simply following the strain rate, which means for a Newtonian fluid, you will just get this sort of a curve coming out. However, again for a non-Newtonian fluid, you will actually have lot of transients, which means the curve will now for non-Newtonian fluid will be like this. And again, just as I spoke earlier in these transient shear experiments, you are trying to get models which actually can predict this sort of curves. On the left, oh, this is just the shear rate versus time. So, yeah, gamma dot. Rho, yeah. Well, so generally it is rho t, but then shear rate is the magnitude of the tensor. So, then you use gamma dot. So, sometimes interchangeably you can use gamma dot and rho. So, essentially you just have some sort of shear rate and it drops down to 0. So, this is the stress relaxation. Now, there are other experiments. There is something called creep, there is something called step strain, and there is something called SAOS, small amplitude oscillatory shear. Now, Professor Joshi might have talked more about the SAOS and other experiments. So, I will limit my discussions to essentially these 3 sets of standard flows and these 3 sets of experiments that you can see. So, what I will try to motivate today is that we can have models which we can have families of models which get progressively better in terms of catching all these various phenomena that you can see. Of course, for every model there is this material function angle and then there is a flow angle. So, for every model you can do flow computations for actual flow problems, but that would be too much to handle in an outline course. I will give some details of the final flow results that you get for various models that we have, but then that would not be covered in details because the derivation would be lengthy. So, what I limit my discussions is the various models and how they are able to capture all these various phenomena that you see. Now, before doing that, I did mention that we have something called material functions and we can measure things from experiments. So, let me figure out the material functions first. Right. So, for steady shear, what we have is 3 types of material functions. Once I define these things, I will probably try to show how the data comes out. Viscosity. Now, as I said, the material it is not a material property anymore. So, the viscosity is actually a material function, and hence the viscosity is a function of the shear rate. Gamma dot is the magnitude of that the rate of strain tensor, which because it is a shear flow, I am just using a gamma dot and it denotes a shear rate. But remember, it is the magnitude of the rate of strain tensor for the flow that you impose. Gamma dot 0 is just the shear rate that you impose. I think gamma dot 0 is this guy. So, essentially what I can write then we have the normal stress coefficients, just as I mentioned a little bit ago. We cannot take the stress values themselves, but we have to take differences in stress. So, there is a first normal stress coefficient, which denoted as psi 1 comma dot. Then we have second normal stress coefficient. So, just for a simple steady shear flow, you have these three material functions that you can define. Now, it is very important in non-Newtonian fluids to have all the three essentially. Viscosity of course, will be a function of the shear rate, and you will see how and why. I will try to explain it. I do not have projector slides, but I will try to draw it, and this would be the driving equation, or this would be the driving data for a class of models itself. Now, the first normal stress coefficient or the second normal stress coefficient, if you take a normal Newtonian fluid which is incompressible, it always predicts that psi 1 and psi 2 both are 0, and you can show that by a simple derivation. You just take a Newtonian incompressible model, calculate for a simple steady shear flow, calculate tau 1 1 and tau 2 2 and tau 3 3, put in the equations, and you can show that for a Newtonian fluid both psi 1 and psi 2 are 0. Viscosity of course, would be the value of the viscosity of the fluid. For a non-Newtonian fluid, typically for polymeric liquids, again of course, this would be of some value which would depend on the shear rate, and I will show how, but psi 1 and psi 2 importantly are also non-zero. Now, this is a very important point. So, the final model that you have should also be able to predict some elastic effects which is coming from these normal stresses, because Newtonian fluids predict that if you have a shear flow, there are no normal stresses, hence there is no psi 1 and psi 2. Non-Newtonian fluids, if you do experiments, typically you have non-zero values of both psi 1 and small non-zero value of psi 2. So, essentially this becomes an important characteristic to judge whether your model is doing all right or not for steady shear flow. Now, this is one thing for steady, which is for steady shear. There are similar material functions for these other two, and I will not show the other three because those will take more time. So, the material functions for shear stress growth, one is, now this is the, let me go for brevity, comma dot. Actually, probably no, because when I do, okay, I will tell you the reason behind it. The way people define it is with the gamma dot square. So, they impose the shear rate and they put the shear rate value here. That is the way people typically define it. When I do simulations and when I try to build my own model, and if I have time I will show it, I do not really care about this gamma dot square. I just measure the shear stresses, and then when I have my own model I will also get the stresses from that model, and then I will just do a simple comparison of the stresses itself. This gamma dot is like a like that constant value which would be there.
Is there any motivation for dividing by gamma dot square? Why not use for?
I see. That I am not very sure. I can check up and see. I do not know if because all of these are actually from data, and you typically measure the stresses. Now, why gamma dot square and why not any other thing, that I am not very sure. I will have to come back later on it.
The reason I am asking about in grains, the shear stress is found to be proportional to shear rate square.
Okay.
So, I am wondering leads to a shear rate square there, or
It might be that the steady value of the shear rate might have some scaling law, and that might have some implications of this gamma dot square. No,
random or
yeah.
motivated?
No, it cannot be random, and I have to come back on it. It cannot be random. It has to be from some data, and they might have seen some scaling, and that might have motivated all this. Now, since it is also there in granular flow, it might be even more general compared to, it's not limited to polymer or granular. It probably is even more general, but I'll check that out. And then I have something in unsteady shear. The shear stress decay is just analogous to the shear stress growth experiments, in which you just have 2 1. There you go. So, you will notice that these are similar experiments and the equations are similar. What this is called is shear stress growth exponent, first normal stress growth coefficient, second normal stress growth coefficient, and these have similar names. Instead of growth coefficients, these will be decay coefficients. I am not writing the names because the names are long, and it does not really hurt by just saying it. There is one other aspect in this stress relaxation experiment, is that it gives you, if you notice the decay of the stress, it gives you some amount of a characteristic time that characterizes this decay of the stress. Now, this characteristic time is also called the stress relaxation time in typical polymeric experiments. So, you do a stress relaxation experiments, you measure the value of stress, and you notice that it decays with time, and you fit the decay to some sort of exponential, and that time constant is actually the relaxation time, which is also called the stress relaxation time of that non-Newtonian fluid. But that the stress relaxation time is not important as of now. It will come up in later aspects. I will probably talk about some details of it in next class, but as of now this is just an information that there is a decay, and the decay constant is the relaxation time that we typically define in polymeric liquids. Okay, so the minus is the brackets in the, oh yeah, that is true. So, all of them have brackets in the numerator. Negative sign comes because of the convention, so that all of these terms are positive. Yeah. Tau 11 and tau 22 would be unequal.
But the shear strain matrix the strain is only in the 2 1 and 1 2 components, and those are equal, and the diagonal components are 0. So, what explains the sort of inequality of these two?
What you are saying is just the rate of strain tensor. Now, what you just said is the description of the rate of strain tensor, in which for shear flow you will have all components to be 0 except this guy, sorry, I will just say this is non-zero and this is non-zero, everything else is 0, right. This was your question. Well, so for a Newtonian fluid, you just have tau to be proportional to the gamma dot. This is a Newtonian fluid, and your thing is right in the sense that if you take a Newtonian fluid, impose this, you do not even need to look at these, impose the steady shear. Once you impose the steady shear, if you take differences of these, they will just be equal and they will both be 0.
So, in the non-Newtonian fluid, even if tau is a function of gamma dot does not distinguish between 2 1 and 1 direction.
Yeah, but
tau 1 1 and tau 2 become different.
the problem of non-Newtonian fluid is this constitutive model breaks down. See here in Newtonian fluid mechanics, this is the constitutive model that you have, which says that the stress generated is simply proportional to this matrix. But what if it is not simply proportional?
So, is it still a function of that matrix?
It will be, it has to be.
So, what I am saying is that if it is equations I don't distinguish between how is it able to distinguish between the 1 and 2 directions, E1 and E2 the direction.
So, this is a function of this matrix and there are functions of these matrix and derivatives of the shear rate and all that. So, yeah, there will be more terms. There will be more terms than just being a function of this matrix, and that functional form may be complicated. So, the final model that you have for non-Newtonian fluids would be much more complicated than this one, and there you can have, I mean, I will probably talk about a second order model in which you have terms which contain gamma dot, double dot, gamma dot and all that. In those models, then you can have a matrix like this, but it can also predict the normal stresses. See, the basic idea of any polymeric liquid is, and it goes back to the steady shear, is that the first and final thing is you should have elastic effects. These two, psi 1 and psi 2, are a measure of the elastic effects. If you take the non-Newtonian Newtonian fluid mechanics, it always predicts that psi 1 and psi 2 are both 0 because of their simple proportionality. But people have repeatedly done experiments, and even for simple shear flow, they have seen that the psi 1 and psi 2 would be positive and non-zero, which means you need to have a model which can predict that sort of a thing. Now, that model is obviously not going to be something like this. That model has to be much more complicated, which should be able to take this sort of a stress tensor and yet shear rate of strain tensor, and yet predict this sort of the first normal and second normal stress coefficients. So, which is why the whole discussion of non-Newtonian fluid flow is going to be very different, because this is the data that exists. Now, I will talk about models one by one, which explains some features of the data, and then we move on in terms of families. But the basic picture is, what I am after are models which can capture the experiments in terms of steady shear, and then these transient experiments in terms of growth, relaxation, and what I have not talked about is similar experiments done with extensional flows. There is only the family of shear standard flows that I have, and the material functions for shear standard flows that I have. An equivalent family exists in terms of elongational flows. Just I defined the elongation flow a little bit ago, and I am not writing those material functions because it will take time. The point is that all of these material functions, once they are defined, people can measure, and people report the measurements in terms of these material functions. And once you have data in terms of material functions, you are looking for models to reproduce all of these material functions. Yeah.
So you are saying that for the Newtonian fluids, always first normal and psi 1 and psi 2 will be 0.
Yeah.
But if Newtonian fluid
for steady shear.
For Newtonian fluid, if you consider tau 1 and tau 2 are different, I mean diagonal elements are different in the stress tensor.
But for a Newtonian fluid, you just have rate of strain tensor, and the fluid is given by mu is a constant, and the rate of strain tensor, and the rate of strain tensor for steady shear is just this would mean the rate of strain tensor would have a 0 here, non-zero here, non-zero here, 0 here, and so on, right. Now, this is your rate of strain tensor. Then you take the value of tau. Tau is minus mu multiplied by the rate of strain tensor, which means if you take the tensor tau, this is 0, this is 0, this is 0. So, 0 minus 0 is 0, again 0 minus 0 is 0. This is what a Newtonian fluid would tell you, but then in non-Newtonian fluids, the first and the foremost thing is these are non-zero, and this is one important feature of polymeric liquids, that these two are kind of non-zero, and they lead to interesting phenomenon as well because of the fact that these are non-zero. The first family of models that we have, unfortunately, is an important family, so I have to speak first about it. Does not capture psi 1 and psi 2, captures the other things. Okay, so these are some data that I mean some sort of trends that we should be able to capture with the models that we have, and these become sort of characterization ways of for non-Newtonian fluids. So, you take a non-Newtonian fluid, impose these sort of flows, and then you notice what kind of a graph that you get. Now comes the fact of the point of modeling, and the primitive models, they started by noting the steady shear viscosity. Now, I have a graph, I will just try to reproduce as well as possible. So, let me see. So, the first family of models is what I call as data driven models. They started by noting the data that we obtain from simple shear experiments, steady shear experiments for eta and psi 1. Well, I am keeping psi 1, it does not really obtain psi 1, and this is for eta. On the x axis, I will have gamma dot, which is typical units are second inverse, because these are flow rates, and on the this is the usual unit for poise and dyne per centimeter square per second and all that. So, this is for eta. I will still not talk about psi 1. These are the typical trends that you obtain from a steady shear experiment for typical polymeric liquids for the steady shear viscosity. So, notice that there is a part when the viscosity is constant. Now, if it is with a Newtonian fluid, viscosity would be constant no matter what gamma dot it is there on the x axis. For a typical non-Newtonian fluids, you typically see that there is a constant part, and then there is a part, before I forget, these are all log scale, and then there is a part which looks like a straight line on this sort of log scale, which means there is a power law. Far away and at very high shear rates, it does show another plateau that I am not showing here. Well, so this is the first sort of data that, and this data is repeated over and over again for various systems that comes out for polymeric systems. It can be dilute or melt or semi dilute. This sort of data always comes out with the trends are similar, quantities would be of course different. Now, what this predicts is that there is a part when the shear rate is too weak. So, this part, the shear rate is too weak. So, essentially it behaves like a Newtonian fluid, and then there is this part where the shear rate is strong enough, deforms and stretches the polymeric elements, and this part is the most important part for polymer processing industry. The most polymer processing applications happen in this region of shear rates. Of course, in a geometry you would have regions where the shear rate is weak, but mostly it is this region which the industry looks at, and this sort of data, it gives rise to some models which are known as more popularly known as the power law model. I will talk about that in a little bit. So, this is the family of model that we call the data driven models, and this has another fancy name of generalized Newtonian fluids. Now, before I move ahead, the trends for psi 1, it might not be relevant as of now, will also be similar. So, there will be a part which is constant, and then there will be a part which is falling down with some scaling law. As of now, we will not talk about psi 1, we will focus our attention on the viscosity and how it changes with the value of gamma dot. And notice that viscosity has a constant part and a log power law part, and then at very high shear rates it again shows a constant part. So, with this background in mind, yeah.
So, it's like you measure tau 1 2 from the experiment,
Yeah.
measure gamma dot from the experiment.
No, we measure tau 1 2 from experiment, and we already have the gamma dot value, because we are imposing the gamma dot.
Right. So, and then you calculate eta by tau 1.
Yeah. So, you measure it, and see tau 1 2 does not have the problem of pressure and tau coupling that I talked about, because pressure does not even appear in tau 1 2. Pressure is only contributing in the normal stresses. So, for tau 1 2 you just take the value of tau 1 2 divided by the gamma dot, and then you get a value of the viscosity, and then you plot the viscosity with gamma dot. Okay. So, this gives rise to the first family of models, which is the generalized Newtonian fluid. So, this gives rise to the first family of models, which is called the generalized Newtonian fluid, also known as, in short, GNF. Now, all of these fluids actually have a common form. If you notice the Newtonian constitutive equation, this would be, it would be written like this, where gamma dot is of course the rate of strain tensor, and for a generalized Newtonian fluid, instead of the material property mu, what we have is a material function eta. So, we will replace it with eta with gamma dot. So, instead of mu, all we do is replace the mu with a function, which is the viscosity function, and this viscosity function actually is more empirical in nature. So, as of now, for this class of models, the viscosity function is more data driven. So, we just look at the data and we put a function, and there is some constraints on the final constitutive model that you get, in the sense that of course, all of these are second order in terms of tensor order, but this proportion of this proportionality function that you have, it should be a function of the invariant of the gamma dot tensor. So, if the gamma dot is a whole tensor, so this proportionality function that you have should be a function of invariance. So, that if you rotate your coordinate system, things do not get perturbed. Now, which means that for a steady shear flow, the only invariant, I mean the usual simplest invariant that comes out for which is relevant for a steady shear flow is this gamma dot, which is the magnitude of the. So, I will just write this gamma dot here is the magnitude of the rate of strain tensor. The magnitude is the double dot of the rate of strain tensor divided by 2 and take the square root. So, this family of models is the data driven set of models, in which we have a viscosity which is a function of gamma dot, but this gamma dot is the magnitude of the rate of strain tensor. So, that is in summary generalized Newtonian model. So, if you use it now, so now that we defined the generalized Newtonian fluid, without going into the details of this function, there are some generic comments that we can make. If you say there is a steady shear flow, so let us go back to the steady shear and then see what we achieved by putting this functional form instead of a constant. So, for steady shear, I have now tau is equal to gamma dot, so 0. So, the stress tensor would now look like this for a steady shear flow, which means that if you now go back to the material functions again and try to compute the material functions, this would be tau 2 1 by gamma dot. Typically, it is denoted as gamma dot 0, because of course, the shear rate you impose is known, and this would mean you are getting back the function which is gamma dot. So, in terms of viscosity, you just trivially get back the functional form that we impose in the model itself. So, essentially this means that if you are data driven and your driving data was the viscosity versus gamma dot curve, you will get back that functional form here for the viscosity. However, using the definitions that we used earlier for psi 1 and psi 2, which are important for elastic effects, and these elastic effects are in turn important for phenomena like Weisenberg rod climbing. So, you will note that for any generalized Newtonian fluid, I have not yet put any form to the gamma dot, gamma as a function of eta as a function of gamma dot. So, for any general non-Newtonian fluids, generalized Newtonian fluids, the psi 1 and psi 2 are still 0. What is good is that you can recover for the viscosity function, because you have imposed it, because it is data driven. What is bad is it still does not have enough in it, because it is of its empirical nature, still does not have enough in it to predict non-zero values of psi 1 and psi 2, which are a regular feature from experiments. So, this is in short its advantage and failure. The polymer processing industry is okay, because most of the polymer processing happens in high shear rate regions, where you do have the function, and that function itself can help you build the flow profile and all that. Well, so now, so there are some models to discuss within this family, some important models. Okay. So, one is the, you would probably almost all of you know, that there is a, and I showed it in itself. So, there is a power law model which predicts the eta to be this one, where m is the consistency index and n is an exponent, which is coming from the data that we noticed earlier. So, yeah, so this n would be from the data, and this part you fit this part and you will get an exponent. Okay. The next, so in this family, this is the Cary-Yasuda model is a little bit more complicated version of the power law model. Again, it is a data driven model. You are looking at the same data, but instead of just fitting the power law portion, you are looking at the data and trying to fit all the portions together. So, you will have a plateau at low values of gamma dot, you will have a plateau at higher values of gamma dot, you will have a sort of power law portion as well. All of this is embedded in the Cary-Yasuda model. Again, it is an empirical model, but what happens is this has more fitting parameters, which makes it complicated to use. Now, eta 0 is the constant viscosity at low shear rates, eta infinity is the constant viscosity at very high shear rates. So, this is eta 0, this would be your eta infinity, and this lambda is a time constant, which relates back to the relaxation time of the sample. Again, this is data driven, but a little bit more complicated than power law, which makes analytical computations much impossible with Cary-Yasuda compared to power law. So, the power law, there are some classic predictions. One of the most classic predictions in for chemical engineering is that in a pipe flow, in the normal pipe flow, in which the Newtonian model predicts a parabolic profile. Sorry about the, it is not really like a parabola, let me redraw it. When you use something like a power law, this profile would change to a bit more flatter profile. The more the value of n, the more flatter it would be. These are some of the classic examples. This is of course for a pipe flow in which fluid is flowing downwards through a pipe, and there is a pressure drop from a section to another section. So, pressure driven pipe flow, the velocity profile becomes much more flatter at the center when you use power law, and this is one of the classic results of power law which we teach in classes. Of course, this derivation will take a long time because of the no velocity is the fluid is flowing down. Oh, yeah. So, what you can do is, I think I flipped it. Yeah. So, now I think I am consistent. So, power law would actually be like this. So, the more the higher the value of this index n, the flatter would be the curve that comes up. And in similar applications, it is not only pipe flow. Yeah, will V. This is V and this is R. And you know, there will be a no slip boundary condition at high R. This is the center R 0. So, and it is symmetric about, of course. well, you don't need to, it's a 0 to r, that is all you have. For a flat plate, of course, you need the other side as well. They should go to 0 at the same r. That's true. Something like this, yes, because of the no slip boundary condition. Now, what I wanted to highlight is that the nature of the flow itself, the velocity profile itself, changes when you put in such adjustments that you get from the data. So, here you have done some adjustments to the data. You have seen the functional form of the viscosity with respect to gamma dot. You have put that functional form in, and as a result, with the power law, because of its relative simplicity, you can still do analytical computations and get velocity profiles like this. So, this is a separate exercise in itself, but with the Cary-Uyashuda, it is a little bit more sophisticated model, because it can capture the data, it can fit the data a little bit better, but with the Cary-Uyashuda, you have no flexibility in terms of analytical computations. It is impossible to do analytical computations, mostly you resort to numerical methods with this. And then there is a third important class, which of course we also kind of teach in classes, which is important for yield stress fluids. One of the most well known yield stress fluids is of course blood, which has a weak value of yield stress. So, this is the third, one of the more important classes within the generalized Newtonian fluid. Now, notice that all of these are, there are some kind of empirical things built in, there is no first principles going on. It is just that I have to correct the viscosity for steady shear. So, I correct it in various ways depending on what data I have. So, one of the more classic examples of Bingham model flow, flows is through a pipe you will get a plug flow region, and then you will have the normal Newtonian region. Similarly for other geometries, but then the limitations are even greater, in the sense that since all of these are driven by the data coming from steady shear, what happens is for other type of flows like elongational flows and all that, the predictions are awful, they do not match at all. And plus you will notice that I have a problem in the material function, because the elastic effects are not shown by the generalized Newtonian fluids. Of course, the viscosity function is captured well, because we have put it that way. The other problem of course is this is steady shear, and
This is like a power law with
which one?
This one is like a power law with the yield circle.
No. This is a power law. This is a tau I is a constant. This is the yield stress. Yeah. So, this is not a n equals to 0. What n equals to 0? Oh, okay. This is just a Newtonian. Okay, what this Bingham model says is that there is a yield stress. Below the yield stress, the fluid will not flow. Above the yield stress, it flows, but it flows exactly like a Newtonian fluid. So, it is rate independent. Yeah, but if you take the viscosity and if you multiply it with the shear rate, then this guy would go away. So, the Bingham model is if you have the stress versus the stress. So, in Newtonian it would be, this would be Newtonian, right, and in Bingham it would be Newtonian with an yield stress. So, this is just a different representation of the Bingham.
Right, but that line could also be horizontal, it could also curve up.
Yeah, all that all different.
Does it necessarily have to be Newtonian post yield?
No, but that is a separate class of models. So, that is called the Herschel-Berkeley, and yeah, see the problem of Herschel-Berkeley is because of the power law nature. So, in a Herschel-Berkeley fluid, you are exactly right. the Herschel-Berkeley fluid is there would be a yield stress, but then it can be something like this, it can be curved. Now, the problem of this is the computations are a little bit more difficult, and but for some simple flow problems you can still do it, but anything beyond a simple flow problem it becomes a little bit more tedious. Now, Herschel-Berkeley is very I think it is very relevant for the petroleum industry, and Bingham is the typical generic fluid that we have which has yield stress. Anything beyond you need something like a Herschel-Berkeley.
The simplest thing that I have come across is that at tau e it just goes horizontally. There is no change in the stress.
Okay, so it's like constant
Rate independent.
rate independent. Okay, but that would be the simplest form of the Bingham, when the simplest form of the Bingham. Zero viscosity, yes, yeah. But typically in chemical engineering we have some viscosity, it flows with something. I think it's important for gels, and gels too do have some viscosity after the yield stress. Okay, now the other thing that I was saying, yes, so all of these do very good in shear flows, in the sense that we have taken the data from the shear flows and we can kind of get back what we put in, because it is an empirical model. However, we did discuss about other kind of shear flows where the shear is not steady, and we might have, again looking for chalks. So, we might have an experiment where the shear rate is suddenly going up, which is the stress growth experiment, and the shear rate is suddenly going down, which is the stress decay experiment. Now, notice the structure of the generalized Newtonian fluid. It is essentially very similar to the Newtonian fluid, except that I am correcting something for the viscosity. Now, all of these experiments, these other classic experiments which has a shear rate which is kind of transient, we know that the typical non-Newtonian fluids would, for this experiment, would show curves like this is what I am drawing for tau, we show curves like this is the tau to 1, and the typical non-Newtonian fluids for this experiment will show curves like this, again for the tau to 1. However, for a generalized Newtonian fluid, because of its simplicity and because of it being a close family member of the Newtonian fluid, what you can only predict is something that the Newtonian model predicts. So, even for the generalized Newtonian fluid, all classes of generalized Newtonian fluids, the shear would closely follow the strain that is imposed. So, if the strain is this way, the shear stress would be following this, and if the strain rate is this way, shear stress would follow it, and it would instantly show a decay. Now, this is the other limitation that we have. So, in terms of modeling, what we have achieved so far, after introducing the GNF class of fluids, we can capture the data more nicely for steady shear. We cannot capture elastic effects though, but then we fail again, we keep failing miserably in these sort of experiments where the shear rate is transient. So, once the shear rate is transient, because of its similarity to the Newtonian model, it will just follow the shear rate instead of showing all these beautiful curves that comes up again from experiments. So, then it poses the next question is, what can I do to address this sort of curves? So, the way people answered it is, for this sort of experiments that you do and for the typical curves that you obtain, here the GNF or the Newtonian fluid, it instantly hits to a new shear rate, whereas in an actual experiment it does not. What they try to understand it in the terms of memory, in the sense that what they assume that the fluid has some sort of memory aspect, which means that the shear stress at a certain time, let us say if I look at the shear stress at this time, even at this time, which is far away from the t of 0, when the shear stress growth started, the fluid will still have some memory of the fact that there was no shear stress beyond a certain time, beyond t 0. So, this is true all over the place for all times. Fluids will have a fading memory of the fact that there was a shear stress which was 0 before the t equals to 0 point. Now, when you bring in this aspect, that the shear stress at a certain time can be a function of not only the strain rate at that time, but also the strain rate at some other time. When you bring in that aspect, then these fluids, the class of fluids is called fluids with memory effects. To highlight the effect of memory that you can have, well, so what I said, let me capture it in a mathematical form. So, in typical Newtonian fluids and generalized Newtonian fluids, what we have is the shear rate at a certain time, suppose this time, will be of course a function of the strain rate at that time. So, this is what we have from generalized Newtonian fluid model, that the shear rate at a certain time will be just proportional to something, and there will be some material function coming in as a proportionality constant. Then people said no, well, since the fluid was almost at rest, it was at rest before t equals to 0, it still remembers that it was at rest, and it has some sort of fading memory of the fact that it was at rest beyond a certain time. To highlight what it brings in, let us just put one more term, and this is actually a little bit instructive to see how this works. So, I included this example. So, what I construct now is again a generalized Newtonian fluid. Let me see if I can, it is not getting better. So, I still have a generalized Newtonian fluid. So, I borrow the structure of generalized Newtonian fluid. What I do is, I have the shear rate at a certain time, I make it proportional to the strain rate at that time, plus I will add a term which has some contribution, which is an earlier term. This is the rate of strain at an earlier time t minus t 0, t 0 can be anything, and this has some contribution which is not 1, you can see, and this has some contribution to the shear rate at the current time as well. Now, if you have a simple model which incorporates a little bit of memory in it, let us see what happens in terms of this experiment. So, I will forget the second one, I will just focus on the shear stress growth, just to highlight the importance of including one memory term in the business. So, before we go to this, with this sort of model, let me first do the steady shear. It is always instructive to do steady shear. So, in steady shear we have the gamma dot tensor, which is usual, if you impose this constitutive model with this steady shear, what you have is as of now t 0 is arbitrary, it is some time which I still do not know. I am just trying to include one more term, so that the memory effect comes up clearly. So, this, and then if you take the material function for steady shear, which is the steady shear viscosity, should be y dot 0. So, this you can I will probably show the tensor as well. And hence this would be psi 1 and psi 2 are again 0, but what it highlights is that for the steady shear I do not do too much of damage, in the sense that the viscosity is just modified by some number. Here I have chosen 0.8. So, viscosity now becomes 1.8 of what it was earlier. That is just a simple modification, it is a simple scale up. The more important point comes when I try to do computations of a fluid which has one memory term for this experiment. And then, so please notice it carefully, because here there are 3 zones that will be divided. So, for the shear startup experiment, I have a profile like this. So, my shear rate is 0 for 0 and a positive value for this, which means I can divide it into 3 different zones. First zone is t less than 0. In this zone, the rate of strain due the first term is of course 0. The second term is also 0. This is for the zone which is t less than 0. Interesting things start when you look at the other zones. So, now you are trying to understand what happens in a time which is in between 0 and the t 0 that you put in your memory model. In that case, one of the thing would be 0, this would be I hope all of you can see. I am just writing a little bit smaller because I have to fit in another one, whereas the other term is still 0. And then there is a third zone which is greater than the t 0. Here I will have both to be non-zero. So, the first term is now both terms are non-zero in this zone, which means that for each of these I can get the stress. So, here the stress tensor would be just simply zero. Then here the stress tensor would be eta. So, this would be this, and then the third one, the stress tensor would be accordingly eta. Both the terms are will of course contribute, because both the terms are now non-zero. So, this would be, so if I can write the final result, you got the picture. So, I will just write the final result here, and this would be minus eta and here this would be minus 1.8 eta. Okay, now which means that now notice the definition of eta plus. Eta plus is your essentially the stress growth viscosity, which is tau divided by some gamma dot. But even if you just notice the value of the stress and then just notice the value of the shear stress out of this tensor, what you can now see, what the simple model with one memory term, what this will predict is that initially it would be 0, there would be some value in intermediate, and then there will be some value here. So, I will circle the points. What we have achieved earlier with a simple GNF was, for the stress growth experiment, I will have a curve like this, which is just following the strain rate, because strain rate increases abruptly. So, the stress also increases abruptly. Here we added just one memory term, and what we obtained is of course a final value, an initial value of 0, but also an intermediate value here. So, in a sense we have some sort of this sort of curve coming for a constitutive model which has one memory term which has an arbitrary T 0 in it. Just an arbitrary factor. As of now, this is just instructive, is an instructive factor. As of now, it has no meaning. Okay? What I wanted to do is I added one memory term to highlight the fact that if you add one memory term, earlier it was just 0 and the final value. Here you add one memory term, you have 0, the final value, and then intermediate value. Now, conversely, if you had infinite such terms in here, infinite such memory terms, because memory terms cannot be just limited to one time, which is a one past value of time. There can be infinite number of memory terms with its own weight added to it, and we will have the notion of fading weights. Once we have such a memory equation with infinite terms with its own fading weights, what we can do is, or what we can expect is this sort of a curve coming out, and this does come out for a memory fluid which has infinite terms here. Now, this is the first time probably you are hearing the term memory fluid, but this sort of memory fluid is not uncommon. In fact, you have heard about a memory fluid, not in a way that it is a memory fluid, but in some other fashion. So, let me erase this. Let me highlight what we achieved so far. So, we had steady shear, experiments. Steady shear experiments for non-Newtonian fluids show some non-zero values of psi 1 and psi 2, which the generalized Newtonian fluids, which is the first class of models, do not capture. Now, we have the other experiments which are shear stress growth and of course, shear stress decay, which I erased. Again, the generalized Newtonian fluid class of models do not capture these experiments, which involve transients. Now, how do we go to model these transients? We added one memory term in the generalized Newtonian value Newtonian fluid format, and what one memory term achieved is it gave us one intermediate point. Conversely, if you could have added 10 more terms, you would have got 10 more intermediate points. What this means is, if I had a proper fluid where I have infinite number of memory terms, I would be able to get a smooth curve which goes to a steady state, which is exactly what my experiments predict. Now, you did hear about a memory fluid, not in the way that it was a memory fluid, but in some other fashion. So, the earliest fluid that we know captures the effect of memory, and it does not talk about memory when it captures it, is what Professor Joshi would have covered. So, I will keep this, I will keep this too, I will write here. So, next question is, when do we have a model which has infinitely many memory terms? The answer is yes, and the earliest model that we have in such applications is the familiar Maxwell model. So, Professor Joshi would have done the Maxwell model, and he would have said that a Maxwell model means there is a spring and then there is a dashpot. So, if you have a viscoelastic material, you can model the viscoelastic material as a series of spring and dashpot. If you have a single spring and a single dashpot, you get the following Maxwell model. If you convert naively to a tensorial form, the same Maxwell model, which involves a spring and a dashpot, in the tensorial form this would come out to be true. Now, he might have talked to you about this sort of a Maxwell model, in which I have a concept of a relaxation time, which is given by lambda, and then a steady shear viscosity, which is given by eta 0. These are the parameters of the Maxwell model that goes, but the derivation of the Maxwell model again goes back to a spring and a dashpot. Now, it does not really look like a memory fluid as of now. Well, when you take the tensor form and then you do some, it will convert it to an integral form. The first thing you can do is multiply both sides by e to the power t by lambda. So, then I am skipping a few steps in the interest of time. So, then you can write this to the power t by lambda dot, and then if you integrate from minus infinity to time, the current time t, and then if you take the normal assumption that the stress at minus infinity is finite, what you would finally get is this sort of an equation, minus t by lambda, minus infinity, t is the current time, well. So, now let me rearrange this in a little bit better fashion. So, I will have the final form to be now. So, if you rearrange the usual Maxwell model, which is a differential model, to this integral form, what you would now see is that there is a bracketed, there is an integral first of all, which means that there is a summation of many terms. The integral means there is a summation of many terms starting from minus infinity to the current time t. So, the integral, this is the argument of the integral. So, do not get confused between t dash and t. T dash is the current time, t dash is t is the current time, t dash is just an integral argument for the integral. And you will notice that effectively then the stress is a summation of many terms of the strain rate at all times from minus infinity to t, with a function which comes before the strain rate. This function is nothing but a weight function which gets added to it. So, if you open up the integral, it would be a summation of infinite terms with a proper weight function. So, essentially this is, if you look at it this way, it is just a constitutive model with infinite memory terms, which actually predicts this sort of continuous monotonic approach towards the final steady state value. So, I will probably stop here. So, this is the point where the memory fluids come in, and with the memory fluid we can actually, what we can achieve is explain this sort of graphs, not the overshoots, but this sort of graphs which monotonically goes towards the steady state. So, first we were able to achieve certain things with the steady state material functions with generalized Newtonian fluids. Then we had the concept of memory, and then I will talk more about, I will start from here itself, and we had something which is a well known model, but put in a different form. It is a memory fluid, and then the memory fluid, all those memory terms would help you to capture the stress growth with time, and conversely the stress decay with time as well, in a smooth fashion to a steady state. So, that is where I stop here, and then tomorrow we will talk about the limitations of this and follow up models.